The ocean under a full moon is a different world. Its surface glows faintly silver, and every ripple carries a mirrored shimmer that flickers across the shallows. Below, the light pierces farther than usual, stripping away the deep sea blues that dominate on darker nights. On the outer edge of the reef, where the coral shelf collapses into open abyss, this brightness transforms the ecosystem. Shadows that once offered safety to resting fish vanish. Sea turtles, which rely on dark cover to rise and breathe, find themselves exposed in a corridor of glowing water. It is here, along this luminous boundary between reef and deep ocean, that the tiger shark begins its patrol. The tiger shark is a creature designed for ambiguity, neither a full-time deep hunter nor a shallow water specialist. Its world is the margin, the place where gradients form. Warm meets cold, current meets calm, light meets dark. On moonlit nights, the shark's range expands across miles of reef edge, tracing the contours of the underwater landscape like a moving shadow. It follows the boundary where the hard limestone shelf drops sharply into blue emptiness, a region scientists call the reef wall. This is the ocean's conveyor belt of life, where tides, temperature changes, and turbulence funnel drifting prey into narrow channels. For most predators, the full moon is a disadvantage. Brightness exposes movement, turning stealth into vulnerability. But tiger sharks invert that rule. Their dark vertical stripes, faint in daylight but perfectly tuned to break up their outline in silvered light, scatter the moon's reflection into soft gradients that mimic the rippling surface. When viewed from below, the shark's body merges seamlessly with the shimmer above. Its hunting advantage comes not from invisibility, but from becoming indistinguishable from the environment itself. In the stillness of night, the reef's pulse does not stop, it merely shifts tone. Daytime schools of parrotfish and surgeonfish retreat to crevices, pressing their bodies tight against coral. Many of them secrete mucus cocoons, thin, transparent veils that mask their scent from nocturnal predators. But those defenses work best against reef specialists like moray eels or hunting octopuses that rely heavily on chemical detection. Against a tiger shark, whose sensory suite spans electric, acoustic, and hydrodynamic domains, such camouflage offers little safety. The shark's snout is embedded with ampullae of Lorenzini, tiny gel-filled pores that detect the faint electrical currents of muscle contractions and even the flicker of a heartbeat. The moonlight provides visual cues. The ampullae provide direction. The patrol begins slowly. The shark swims cross-current along the reef face, its massive body moving with deceptive ease. Each flick of its tail sends a rolling pulse of energy through the water, enough to propel it meters at a time without visible effort. To conserve energy, it uses the current seams, narrow corridors where opposing flows meet and cancel each other. These seams act as conveyor belts, letting the shark glide with minimal drag. Within this zone, water carries scent, sound, and temperature gradients in complex eddies. The shark reads them as effortlessly as a bird reads wind. The full moon amplifies the feeding rhythm of the reef. Tidal surges triggered by lunar pull push small fish, crabs, and even sleeping turtles from their hiding places. Juvenile turtles, resting near the surface to warm their bodies, are particularly vulnerable. As the tide ebbs, it creates a slow outbound drift along the drop-off. The tiger shark positions itself against this flow, crosswise to the current, intercepting anything swept seaward. Each pass is timed precisely, not too close to the coral, where maneuvering space is limited, and not too far into open water, where prey disperses. Its route forms a moving trap defined by light, current, and instinct. To understand how the tiger shark exploits moonlight, one must consider how light behaves underwater. As it filters through the surface, the bright lunar glow becomes polarized. Its waves align, creating patterns invisible to most fish, but not to the shark. Recent studies suggest that many large predatory sharks can detect polarized light, using it to discern the orientation and movement of objects even in low contrast. Under a full moon, the shark's eyes, rich with reflective retinal cells called tapetum lucidum, gather and amplify this faint polarization. The effect is like switching from grainy monochrome to high definition. Every flick of a fin, every twitch of a sleeping parrotfish becomes legible in the haze. The tiger shark's hunting strategy here differs from the high-speed chases seen in open water. On the reef edge, precision outweighs speed. The shark approaches potential prey at an oblique angle, staying just beyond the lateral line detection range, roughly 1 to 2 meters in small fish, farther for larger animals. It tilts slightly to one side, the pectoral fin adjusting like a trim tab, reducing its profile while maintaining lift. When the moment comes, the lunge is short and explosive, a few meters of acceleration powered by the massive caudal fin, combined with a half roll that aligns the jaws for a sideways strike. The attack sequence is brutally efficient. The shark's upper jaw, loosely attached to its skull, swings forward at the moment of impact, extending its bite radius. Serrated teeth, designed for slicing through thick armor and shell, meet with mechanical precision. Against turtles, one of its favored prey, the tiger shark employs an astonishing tactic. It does not bite blindly. Instead, it first bumps the shell to test for weakness, then strikes at the softer edges near the flippers or the carapace's hinge points. The initial bite immobilizes, the second dismembers. In the darkness, only a brief cloud of phosphorescent plankton betrays the violence. Not all hunts succeed. The same moonlight that aids the shark can alert prey. Green sea turtles, for instance, adjust their surfacing behavior based on lunar brightness. On full moon nights, they often choose steeper reef slopes or deeper channels for rest, where light penetration is reduced. This constant evolutionary arms race between vision and countervision, exposure and adaptation, defines the nocturnal reef. But even when prey eludes capture, the shark gains valuable information. Each patrol refines its mental map of the reef, where currents split, where prey densities peak, where tidal noise masks its approach. Over time, it becomes less a visitor and more a feature of the reef's hydrodynamic architecture. The moon also influences physiology. Under bright lunar conditions, tiger sharks exhibit elevated activity levels and expanded range. Biotelemetry data show that their vertical movements correlate strongly with the lunar cycle. During full moons, they stay shallower, exploiting the light window. During new moons, they descend to deeper ledges, relying on electroreception instead of sight. This adaptive rhythm balances risk and reward. Staying near the surface increases hunting success, but also energy cost, as buoyancy control and exposure to warmer water raise metabolic rates. To offset this, the shark alternates between active passes and resting glides, using downwellings to sink effortlessly into cooler, denser layers before rising again to patrol. Every sense the tiger shark possesses serves a role in this dance of light and current. The lateral line, a chain of pressure-sensitive canals running from head to tail, registers the micro-vibrations of passing fish even before visual contact. The eyes, adapted for both low-light vision and rapid refocusing, process contrast far more efficiently than human eyes. The nostrils, or nares, can detect a single drop of blood in millions of liters of seawater, but they also pass complex chemical signatures, allowing the shark to distinguish between species, stress levels, and even reproductive states. On a moonlit night, these senses fuse into a singular awareness, a three-dimensional picture of motion, scent, and sound, built in real time. What makes the tiger shark remarkable is not its aggression, but its patience. Despite its fearsome reputation, it rarely hunts through continuous pursuit. More often it waits, letting physics do the work. The moonlight creates the stage, the tide sets the rhythm, the shark simply reads the performance. When a sleeping turtle drifts too close to the drop-off, or a wounded grouper is flushed from its crevice by current, the predator is already in position. By dawn, the moon fades and the balance reverses. Reef fish begin to stir, emerging from their nighttime shelters as sunlight penetrates the shallows. The tiger shark descends, leaving the illuminated reef edge for deeper, cooler water. Its metabolism slows, and the glow of its eyes vanishes into the blue. The reef resumes its daytime order, as if the night's predation never happened. Yet the cycle will return, each full moon reshaping the reef's behavior, redrawing its boundaries of fear and opportunity. In the end, The tiger shark's mastery lies not in brute strength, but in synchronization. With tides, with light, with the physics of moving water. It is a hunter that has learned to let the ocean's rhythms dictate its own. Where others see exposure, it sees clarity. Where others seek darkness, it uses light. On those nights when the moon lays its silver path across the sea, the tiger shark becomes both shadow and current, the silent enforcer of the reef's hidden order, gliding through the boundary where the living light fades into endless blue. On a still tropical night, the sea lies glass flat under the moon. Each ripple carries a mirrored shimmer, and the surface seems so calm it could be mistaken for air. But beneath that serenity, the most venomous predator in the ocean is at work. The box jellyfish, an organism both primitive and precise, drifts through the shallows with purpose, its nearly invisible body suspended in the luminous water. There is no sound, no visible pursuit, only a slow choreography of tentacles in motion. This is the moon's curtain, a silent, shimmering trap woven from biology, light, and the physics of the tide. When the moon grows bright and the water runs clear, the box jellyfish comes close to shore. Scientists once thought these movements were random, dictated by wind and chance, but careful observation has revealed an intricate rhythm tied to the lunar cycle. On certain phases, especially around the full moon, jellyfish congregate along beaches and mangrove-fringed bays. They are not drawn by light alone, but by the combined geometry of tide, current, and prey migration. As the tide rises, it carries small fish and crustaceans inland. As it falls, it funnels them seaward again. The jellyfish positions itself within this conveyor belt of life, a passive hunter perfectly aligned with moving flow. To understand why these nights are dangerous, for fish, for plankton, and for any unlucky swimmer, one must first understand how a creature without a brain can plan an ambush. The box jellyfish is not a mindless drifter. Box. It is equipped with an astonishing visual system. 24 eyes arranged in clusters called rhopalia, each designed to interpret a different aspect of its environment. 4 of these eyes are surprisingly complex, complete with corneas, lenses, and retinas, similar in principle to the eyes of higher animals. They do not form detailed images, but detect contrast and orientation. Under moonlight, this becomes crucial. Where other jellyfish rely on touch or chemical cues, box jellies see. They orient to horizon lines and shadows, maintaining a stable vertical position even in shifting current. Their vision allows them to hunt not by proximity, but by silhouette, a form of contrast predation. On clear, calm nights, when the moon floods the shallows with pale light, small fish and prawns stand out as dark, moving shapes against the reflective seafloor. The jellyfish drifts below them, its translucent bell almost invisible in the dim glow, while its tentacles, long, thread-like filaments extending several meters, form a nearly undetectable fence. Each tentacle is a weaponized organ, lined with thousands of specialized stinging cells called nematocysts. When triggered by contact or certain chemical signals, these microscopic capsules fire tiny harpoon-like threads that inject venom into the target in less than 1,000th of a second. The venom acts on multiple fronts, paralyzing the prey's muscles, collapsing its nervous system, and attacking heart tissue. For small fish, death comes in seconds. For humans, depending on the species and dose, it can cause cardiac arrest within minutes. Yet this lethality is not wasteful. The venom's potency allows the jellyfish to immobilize prey instantly, preventing the fragile tentacles from tearing under the strain of struggling victims. Evolution has optimized both chemistry and mechanics to suit a creature with no skeleton, no brain, and no margin for error. The term box jellyfish covers several species, but in northern Australian waters and throughout Southeast Asia, Chironex fleckeri reigns supreme. It is as close to an apex predator as a gelatinous form can be, large enough to hunt fish, fast enough to swim against the tide. Unlike most jellyfish that drift passively, Chironex propels itself with rhythmic contractions of its bell, reaching speeds up to 2 meters per second. The movement is surprisingly deliberate. By pulsing one quadrant of its bell at a time, the jellyfish can steer, accelerate, or reverse course. This fine control allows it to patrol the same estuarine channels repeatedly, often returning to favored hunting zones on successive nights of similar tidal and lunar conditions. The moon influences not just where they hunt, but how they hunt. During darker phases, when water is turbid and light diffused, the jellyfish extends its tentacles widely, forming a drifting net that maximizes contact chance. But when the moon brightens and visibility increases, it changes strategy. The tentacles retract slightly, forming a more compact array positioned to intercept fast-moving prey drawn toward the reflections near the surface. Laboratory studies show that box jellies adjust venom output depending on prey type and size, a level of physiological modulation astonishing for a creature without centralized control. Against small crustaceans, they release less venom. Against larger fish, they deliver the full biochemical arsenal. Even the firing sensitivity of nematocysts fluctuates with environmental factors such as water clarity, salinity, and current speed. The phrase, calm, clear, moonbright, once an innocent description of a perfect beach night, has become a warning along the coasts of Queensland, Malaysia, and the Philippines. It marks the nights when swimmers face the highest risk. The conditions that make the sea appear beautiful also make it deadly. In still water, the jellyfish's tentacles hang straight and undisturbed, forming vertical barriers invisible to the eye. Under moonlight, the transparency of the bell becomes total. Only the faintest ripple betrays its motion. Even artificial light can play a role. Coastal towns and resort lights reflect across the lagoon, confusing both prey and predator. Small fish gather around illuminated shallows, mistaking them for moonlit pathways, and the jellyfish follow. In these moments, the boundary between natural and human-made light collapses, and the predator thrives in the confusion. For local marine ecologists, this lunar behavior is more than spectacle. It is a lesson in how tightly evolution binds organisms to cycles beyond their control. The moon dictates not just tides, but visibility, current velocity, and even the chemical gradients that guide prey. For the box jellyfish, these are not random environmental shifts, but precise signals. It times its breeding migrations to the same lunar calendar. During the wet season, when rivers flood and salinity drops, adults gather near estuary mouths. Their life cycle completes within a year. Adults die soon after reproduction, while larvae, called planulae, settle on submerged surfaces and develop into tiny polyps. When conditions align, often triggered by temperature and light, these polyps release miniature medusae into the current, continuing the cycle. Despite its reputation, the box jellyfish is not an indiscriminate killer. Its hunting efficiency is built on economy, not excess. Each nematocyst can fire only once, and replacing them is metabolically costly. Therefore, the jellyfish must manage its arsenal carefully. By relying on vision to target prey instead of firing blindly, it preserves its venom supply. This selective precision is part of what makes it so dangerous to humans. Our limbs and torsos are large enough to trigger massive, synchronized discharges from multiple tentacles, overwhelming the body with toxins it never evolved to resist. In the broader ecology of the coast, the box jellyfish plays a subtle but crucial role. By preying on small, fast-breeding fish and crustaceans, it helps regulate populations that would otherwise explode during plankton blooms. Its presence shapes the behavior of entire food webs. Fish species have evolved to recognize the faint optical distortions caused by its tentacles. Some crustaceans, particularly prawns, adjust their migration routes and timing based on lunar brightness to avoid peak jellyfish activity. Even the seasonal movements of sea turtles, which feed on jellyfish, appear to counterbalance these cycles, a delicate interplay of predator and prey orchestrated by the gravitational rhythm of the moon. As the night deepens and the tide turns, the curtain begins to dissolve. The jellyfish retracts its tentacles and drifts seaward with the receding current. The same moonlight that granted it dominance now exposes it to open ocean predators like turtles and larger fish. Its transparency, once an advantage, becomes vulnerability. Yet the ocean forgets quickly. Within hours, the tide will shift again, the prey will return, and the cycle will resume with the next lunar pulse. To witness this process, to see the sea illuminated by moonlight, and know that death drifts silently within it, is to grasp how finely tuned evolution can be. The box jellyfish does not stalk, chase, or think. It responds to ancient patterns of tide and light that have guided it for millions of years. Its hunting ground is not a fixed place, but a condition: calm water, clear visibility, and the silver path of the moon overhead. On those nights, the ocean glows like liquid glass, and the line between beauty and danger vanishes. Beneath the moon's curtain, the box jellyfish waits, a ghostly reminder that even the simplest creatures can master the most complex rhythms of the earth. Night along a tropical shoreline is rarely still. The tide sighs through the mangrove roots, and the surface of the water glitters under the fractured light of the moon. Each small ripple throws a shimmer, and every glint seems to move of its own accord. To the human eye, it is mesmerizing. To a small fish, it is disorienting. Beneath this rippling mirror, invisible to all but the most careful observer, a sea snake moves, slow, deliberate, and perfectly camouflaged within the chaos of reflection. Its body, glossy and muscular, slides just below the surface film, tracing the boundaries of light and dark as though following a map written in moonlight. This is Hydrophis, one of the true sea snakes, a lineage of reptiles that traded land for ocean millennia ago. It breathes air yet lives almost entirely underwater, a contradiction turned into mastery. The surface, for most predators, is the most dangerous layer of the sea. It is where visibility is highest, where noise and vibration are amplified, and where the boundary between air and water acts like a wall of glare. But the sea snake has turned this limitation into strategy. It uses the glitter itself, the constantly shifting patchwork of reflections caused by wind, tide, and lunar angle, as living camouflage. From below, the body's scales scatter light in polarized waves, blending with the glimmering surface. From above, its serpentine form merges with the dappled moonshine reflected off the water. Even the patterning of its body, alternating bands of pale silver and black, is tuned for this world of contrast, where light bends and refracts in every direction. Every few minutes, the snake must surface to breathe. Unlike fish or eels, it cannot extract oxygen from the water indefinitely, though it has evolved ways to stretch each dive to remarkable length. Nearly a quarter of its oxygen uptake occurs directly through the skin, thanks to an unusually dense network of capillaries that run just beneath the scales. Still, air is life, and surfacing is inevitable. Each ascent must be calculated with care. Rising too fast exposes it to sharp-eyed seabirds or predatory fish. Waiting too long risks suffocation. So the sea snake times its breaths to rhythm, specifically the rhythm of the tide. In tidal creeks and estuaries where these snakes often hunt, water moves in pulses, surging, slowing, then reversing. Between each surge lies a brief lull, a slack tide. During this pause, surface disturbance drops, and currents flatten just enough for the snake to rise silently. It pierces the surface with its snout, a small valve-like nose perfectly shaped to break tension without splash. A single inhalation fills the elongated lung that runs nearly the entire length of its body. This lung is more than a breathing organ. It acts as a buoyancy chamber, allowing the snake to fine-tune its depth with minute adjustments in air volume. When full, it can hover effortlessly beneath the mirror layer, its head angled upward, waiting for prey to drift by in the silver haze. The prey are often fish, mullet, anchovies, or juvenile reef species, swept inland by the rising spring tides. In these narrow creeks, the water becomes a corridor of abundance, but also a trap. The sea snake positions itself where the tidal flow meets a bend or constriction, a place where the current compresses schools of fish into predictable paths. The snake's strategy is simple in concept but exquisite in execution. It uses the brightness of the surface as cover. Fish that rely on polarized light to detect predators from below are effectively blinded by moonlit glitter. The contrast sensitivity of their eyes, so useful during the day, fails them here. The snake waits directly beneath this glare zone, invisible against the flashing ceiling. When the moment comes, it moves with startling speed. The strike is short-ranged, driven by precision rather than power. The jaws open wide. Hinged on flexible ligaments, that allow each side to operate independently, an adaptation borrowed from its terrestrial relatives. But unlike land snakes, the sea snake cannot afford prolonged struggles or wasted energy. Its world is one of constant motion, and it must feed efficiently. The fangs, short but sharply curved, deliver venom optimized for marine prey, a neurotoxic cocktail that stops movement almost instantly without tearing fragile tissue that might cloud the water and attract scavengers. The snake grips, injects, releases, and waits. Within seconds, the victim stiffens and sinks, and the predator coils upward to swallow it whole, aligning the fish with the curve of its body to ease passage down the throat. Venom in sea snakes is among the most potent in the animal kingdom, though its purpose is pragmatic, not aggressive. It acts quickly to paralyze prey before escape, a biochemical efficiency born from necessity. The high concentration of neurotoxins, coupled with enzymes that disrupt respiration, means the snake can subdue an animal several times its size in seconds. Evolution has fine-tuned this system to perfection, enough venom to immobilize instantly, but not so much that it wastes its limited supply. In ecological terms, this balance is critical. The sea snake cannot produce venom indefinitely. Each bite requires days to replenish, so selectivity and timing are essential. As it hunts, the snake moves with uncanny control. Its flattened, paddle-like tail, one of its defining features, acts as a hydrofoil, generating thrust with small lateral flicks. The midsection remains nearly still, allowing for forward movement without visible ripples. In calm water, even a single wave can betray presence, but the sea snake's body displaces fluid evenly along its length, diffusing disturbance. The result is near invisibility, not through color or stillness alone, but through hydrodynamic silence. The glitter camouflage works both visually and physically. On nights with wind-driven chop, when the surface breaks into thousands of moving highlights, the snake's reflection blends seamlessly into the pattern. But on perfectly still nights, when moonlight turns the water into a solid mirror, the snake must adapt differently. In these moments, it hunts deeper, using the underside of the reflective layer as concealment. By positioning itself just centimeters below the surface, it takes advantage of a phenomenon known as total internal reflection. To an observer beneath, the snake's outline disappears entirely, replaced by the dazzling mirror of the water above. Only when it moves, a faint distortion among the glints, does its presence become detectable, and by then, the strike has already begun. Each ecosystem molds its sea snakes differently. In shallow bays, species evolve paler bodies to match sandy bottoms. In darker mangroves, they grow more patterned, echoing the interplay of shadow and leaf. Some species spend entire lifetimes within narrow estuaries, while others venture far into open ocean, diving to depths where light fades to blue. Yet all share the same fundamental dependency: air. The very need to surface defines their ecology. Every hunt, every migration, every encounter is shaped by that single constraint. It forces them into a delicate dance between risk and reward, the constant trade between exposure to the air and concealment below it. During spring tides, when gravitational forces from the moon and sun align, the extremes of water movement reshape entire coastal systems. For the sea snake, these tides dictate opportunity. High surges carry prey inland, and as they recede, they draw them back through tight channels where escape routes shrink. The snake learns these rhythms as instinct, responding to the cycle of lunar light and tidal pulse with remarkable precision. Its internal clock, entrained by environmental cues, guides it to the right place at the right time, night after night. To human eyes, this behavior can seem almost calculated, a deliberate exploitation of optical physics and celestial rhythm. But for the sea snake, it is simply survival written in light and flow. Its world is one of gradients, salinity changing by the meter, current shifting by the second, light scattering by the wave. In this environment, perfection is not domination, but adaptation. Learning to exist exactly at the boundary between visibility and invisibility, air and water, risk and advantage. As dawn approaches, the glitter fades. The moon's silver path dulls to grey, and the first light of morning turns the creeks into gold-green corridors. The sea snake retreats, sinking into deeper pools or burrowing among roots until night returns. Its camouflage, now useless in daylight, gives way to stillness and shelter. Above, the mangroves hum with life, birds calling, insects rising, the day reclaiming its realm. But below, just beneath the surface, the mirror remains, waiting for the next moon to scatter its light, for the glitter to return, and for the hunter to rise once more beneath it. In the balance of light and motion, the sea snake has found its place, not as master of the sea, but as its interpreter. It reads the shimmer, the rhythm, and the pull of the moon, turning them into weapons of stealth. Its glitter camouflage is not illusion, but harmony, the blending of evolution and physics into a single fluid survival strategy. And as long as the moon casts light upon water, the serpent beneath the mirror will continue to hunt within its reflection, unseen, yet utterly present. The ocean's most intelligent hunters rarely chase in straight lines. They shape water itself into a weapon. In the pale light of early morning, a pod of bottlenose dolphins gathers across a shallow bay, their dark dorsal fins slicing the surface in calm synchronization. The tide is swelling, not an ordinary tide, but a spring tide, when the sun and moon align to pull the sea into its greatest extremes. The incoming water moves with silent urgency, funneling through the sand flats in broad, curling streams. Beneath that motion lies opportunity. To the dolphins, this is not a random surge. It is a window of perfect geometry, when the current compresses small schooling fish into narrow arcs. The pod has been waiting for this moment. The timing is not luck. Across much of the world's warm coasts, from the Gulf of Mexico to northern Australia, dolphins have learned to read the lunar cycle as precisely as any mariner. They sense the difference between neap and spring tides not by calendar, but by flow. The texture of moving water, the way sand grains roll along the bottom, the faint hum of the surf's undertow. On these high tides, the sea floods farther inland, filling lagoons and tidal creeks with silvery clouds of baitfish. When the current turns and begins to drain, those fish find themselves trapped between open shallows and receding water. The dolphins move in then, exploiting the compression of life against the falling tide. What unfolds looks like chaos, but it is closer to choreography. A few individuals take position at the perimeter of the bait school, circling slowly to corral the fish. Others patrol the deeper edge, driving stragglers back toward the shallows. These are the herders, experienced adults whose spatial awareness rivals that of any pack-hunting predator on land. They do not simply encircle, they steer, using bursts of sonar clicks to gauge position and adjust formation. Their echolocation allows them to track the density of the fishbowl through walls of mud and bubbles. Even when vision fails, the echo tells them everything: direction, concentration, and gaps to seal. Once the school tightens, the next phase begins. The hitters surge forward, slashing their tails into the sand and silt to lift a thin veil of sediment. The blow looks violent, but it is calculated. Each tail strike releases a pulse of fine particles that rise in a curling column, twisting with the current into a ring. The dolphins repeat the maneuver with astonishing precision, connecting ring to ring until the entire perimeter of the bait cloud becomes shrouded in a vertical curtain of mud. What began as a loose formation now solidifies into architecture, a corral built from fluid dynamics. To an observer above, the scene resembles a blooming halo expanding beneath the water. The edge of the mud ring appears almost solid, a barrier that fish instinctively avoid. But to the dolphins, it is an optical illusion weaponized. The fish see only an opaque wall and panic inward, condensing their ranks. In this density lies their downfall. The dolphins wait just beyond the cloud, mouths open, ready for the signal. With a subtle body flick from one of the leaders, a movement more gesture than command, the catchers surge through the center. The bait explodes upward in a glittering burst of scales, and the dolphins strike, snapping at the compressed ball from below. Each attack lasts only seconds. Then the formation resets. The herders tighten the perimeter again, The hitters rebuild the wall, and the process repeats. In some pods, this ritual continues until the tide has nearly drained the bay. The energy cost is considerable, but the payoff is exponential. Dozens of fish per dolphin, taken with surgical efficiency. The key to this strategy lies not just in teamwork, but in timing. Spring tides amplify everything: current speed, turbulence, and sediment flow. The greater water movement suspends fine particles more easily, allowing the mud wall to form and hold shape longer. During weaker neap tides, the same strikes would fall apart within seconds, the cloud too thin to trap prey. But when the moon stacks the tide to its maximum range, the physics align. The stronger currents lift finer silt from the bottom, and the resulting turbidity lingers like smoke. The dolphins have learned this correlation over generations. Whether by inherited instinct or cultural transmission, a hallmark of dolphin intelligence, they appear at these feeding sites precisely when conditions peak. Each individual in the pod plays a role learned through experience. Juveniles watch from the outer edges, mimicking the movements of their elders, but rarely participating in full strikes. They practice tail slaps on drifting debris or small schools until coordination improves. Over time, these apprentices graduate from follower to herder and eventually to hitter or catcher, roles not dictated by dominance but by skill. In behavioral terms, this division of labor represents one of the most advanced cooperative hunting systems in the marine world, rivaling the complexity of pack hunting wolves or coordinated lionesses. The mechanics of the mud ring are more than spectacle, they are pure hydrodynamics. Each tail slap produces a pressure pulse that dislodges sediment, creating an upward plume. As the dolphin spins, the rotation induces a vortex, which stabilizes the wall's outer edge. Water moving through the vortex shears the silt into a continuous sheet, and surface tension maintains its cohesion long enough for the trap to close. In laboratory models, even small changes in current speed or angle can determine whether the wall holds or collapses, a reminder that the dolphin's success is built on precise physical knowledge of their habitat. Beyond the physics lies communication. Dolphins coordinate these hunts through a mix of acoustic and visual signals, bursts of narrowband clicks to gauge distance, short whistles to synchronize position, and body cues like rolls or pectoral fin gestures to initiate phases of the hunt. Each pod's dialect differs slightly, suggesting local adaptation, a cultural tradition passed down like a regional accent. Some groups even replace mud walls with bubble nets, exhaling streams of air rings that trap prey in clear water when sediment is too coarse or the bottom too rocky. The principle remains identical: shape the environment to shape the prey. As the tide falls to its lowest reach, the landscape changes. Channels that were meters deep an hour earlier shrink to shallow ribbons, and the bait fish are forced into ever tighter pockets. The dolphins shift strategy once more, abandoning the circular wall for linear sweeps. They drive prey into the remaining pools, sometimes even stranding themselves temporarily on exposed flats to grab the last fish before sliding back with the returning swell. This strand feeding, observed in a few coastal populations, pushes their cooperation to its extreme limit, relying on memory of terrain and trust in each other's movements. They must know the precise angle of retreat to avoid beaching fatally. Underneath these hunting displays lies a deeper ecological rhythm. The dolphins are not merely reacting to the moon's pull, they are woven into the tidal pulse itself. Their movements influence prey behavior across entire ecosystems. Fish populations adjust spawning and migration timing around periods of intense dolphin activity. Crustaceans bury deeper in sediment during lunar peaks, sensing pressure changes caused by both the tide and the predators it attracts. Even seabirds, perched along the mangrove fringe, have learned to associate the rising mud plumes with imminent feeding opportunities, diving at the edges of the dolphin rings to snatch fleeing fish. To study this synchronization is to witness evolution at the scale of the ecosystem. The moon's gravitational force, an ancient constant, creates predictable surges in water movement. Dolphins, with brains capable of abstract association, have turned that cosmic rhythm into a foraging calendar. They do not simply hunt during the spring tide, they anticipate it. Research tracking their movements shows increased coastal presence in the days leading to the lunar alignment, suggesting foreknowledge of its approach. The spring tide is not random luck, but an event they prepare for, much as terrestrial predators follow the migration of grazing herds. The final act of the hunt unfolds as the light fades. The bay, once clear, is now a suspended cloud of sediment and organic matter. The dolphins, having fed, slow their movements, lingering in the quieter eddies near the mangroves. Juveniles play with drifting fish bones. Adults surface to breathe in rhythmic unison. The full moon rises above the horizon, casting silver beams across the muddied shallows, the very light that will, by morning, pull the next tide back in. The scene closes not with frenzy, but with calm efficiency. The bay settles, the water clears, and life resets for the next cycle. The mud rings, transient structures built from timing, teamwork, and gravity, dissolve back into the current. The dolphins disperse offshore, carrying the memory of success that will guide their next hunt, when the moon and sun once again align. In this way, they are more than hunters. They are engineers of flow, builders of invisible walls shaped by celestial rhythm. Every tail flick, every spin, every coordinated strike is an act of understanding, of physics, of place, of time. The dolphins do not conquer the tide, they cooperate with it, reading its language written in sand and current. When the moon stacks the sea to its fullest reach, they answer with strategy. And for a few hours, intelligence and nature move in perfect synchrony, mammals born of land turning the pulse of the ocean into a masterpiece of collective design. At the edge of the reef, where deep ocean currents collide with the continental shelf, the water seems alive. It swells, heaves and folds into invisible layers, tides within tides, waves beneath the surface that no sailor ever sees. These are internal waves, immense underwater pulses born from the gravitational tug of the moon. Each new and full moon amplifies them, driving denser, nutrient-rich water upward from the depths. As these hidden waves break against the reef's slope, they inject new life into the shallows, triggering blooms of plankton so thick they turn clear blue water into a greenish haze. And when this happens, the manta rays come. They appear first as shadows, broad, fluid silhouettes gliding just beneath the light. Their movements are deliberate, almost meditative, yet every wing beat has purpose. The mantas are here for the feast, drawn by a convergence of physics and biology that unfolds only a handful of nights each lunar cycle. The reef pass, that narrow channel where lagoon water drains to the open sea, becomes a superhighway of drifting life. Plankton, stirred by the moon's pull and compressed by tidal flow, forms into dense ribbons that snake through the pass. It is a phenomenon dictated not by chance, but by the exact timing of celestial mechanics, ocean density, and topographic shape. The manta rays know these rhythms as intimately as any tide gauge. Each individual, sometimes spanning over 5 meters from wingtip to wingtip, positions itself with surgical precision. They align their bodies into the current, mouths agape, cephalic fins unfurled like curved horns. These flexible appendages, unique among rays, act as flow shapers, channeling water directly into the cavernous mouth. By adjusting the angle of these fins, mantas can sculpt how water enters, focusing dense plankton streams while deflecting debris or turbulence. In effect, they are not simply feeding, they are engineering the flow, turning the moon-driven chaos of the tide into an organized conveyor of food. At the height of the feeding frenzy, dozens of mantas can gather, forming a slow-moving spiral, a cyclone of giants rotating through the same patch of water. From above, the sight is mesmerizing. A vertical carousel of wings, each ray following the one ahead through the same rich filament of plankton. To the casual observer, it looks like cooperation, but in truth it is physics in motion. The first manta disturbs the water column, creating a ring of low pressure and vortices that pull plankton inward. The next one follows, exploiting the concentrated wake, while the third and fourth maintain the flow structure by swimming in tight formation. Each pass thickens the plankton core, creating what oceanographers call a feeding vortex. The system sustains itself as long as the current holds. Why does this happen most dramatically around the new and full moon? The answer lies in tidal amplitude. When the moon and sun align, their combined gravity produces the strongest tidal forces on Earth. These spring tides amplify both horizontal and vertical water motion, enhancing upwelling at the reef edge. In these moments, suspended nutrients rise into the photic zone, where sunlight fuels phytoplankton growth. Within hours, the microscopic plants multiply, and zooplankton, the tiny drifting animals that feed on them, follow. The result is a vertical migration of life, compressed by the tide into narrow ribbons along underwater contours. The mantas do not need to chase. They simply position themselves where the physics does the gathering. What makes manta feeding so extraordinary is the degree of control they exert over something as chaotic as ocean flow. Their bodies are optimized for fluid dynamics. The broad flat wings generate lift as they glide, while the slightly concave ventral surface stabilizes them in turbulent currents. Every movement of the pectoral fins changes the local pressure field, reducing drag while maximizing intake efficiency. The cephalic fins, those graceful spiraling lobes flanking the mouth, function like variable geometry funnels, adjusting the flow's angle of attack in real time. In high-density plankton swarms, mantas roll their fins into tight spirals to increase precision. In diffuse conditions, they spread them wide to capture a broader stream. Each decision balances energy cost against reward, and each motion is informed by sensory feedback from pressure receptors along the skin. When the current intensifies beyond a certain threshold, mantas switch tactics. Instead of solitary gliding, they form organized feeding trains, linear formations that exploit hydrodynamic drafting. The lead manta faces the full brunt of the current, its body creating a slipstream behind it. The following individuals occupy this wake, expending up to 30% less energy. When the leader tires, it falls back and another takes its place. This rotation ensures that the group can feed for hours with minimal fatigue. Such behavior blurs the line between instinct and intelligence. Whether conscious coordination or evolved reflex, it reflects an intimate awareness of water as both environment and medium. Beneath the surface spectacle, a finer choreography unfolds at the microscopic scale. Each gulp of seawater passes through a specialized filter apparatus inside the manta's mouth, a sieve-like structure composed of elastic lamellae. Unlike the rigid gill rakers of whale sharks, these lamellae flex and vibrate in response to flow. The movement causes plankton to separate from the passing water by a mechanism known as ricochet filtration. Instead of clogging the filter, particles bounce off angled ridges and spiral toward the esophagus. It is a self-cleaning design so efficient that engineers studying fluid filtration have modeled industrial systems after it. This adaptation allows mantas to process hundreds of liters of water per minute without fouling their gills, an essential trait when feeding for hours in sediment-laden tidal passes. The feeding event is not constant. It waxes and wanes with the moon's pulse. As the tidal front shifts position, the plankton ribbons move too, sometimes collapsing entirely when the current slackens. When this happens, the mantas disperse, gliding back into deeper water where they can rest or clean themselves at reef stations. These stations, often located near the same tidal fronts, serve as social hubs where cleaner wrasses remove parasites and dead skin. Even here, the rhythm of the moon persists. The same currents that bring food also refresh the oxygen flow and temperature gradients the mantas need for thermoregulation. For marine ecologists, this synchronization between celestial mechanics and animal behavior offers profound insight. Manta rays are not passive participants in the ocean's cycles, they are active interpreters. By tuning their feeding to the physics of tidal fronts, they maximize energy gain in an environment that is otherwise unpredictable. The moon's gravitational pull, a force acting across nearly 400,000 kilometers of space, shapes not only the movement of water, but the survival strategies of one of Earth's most majestic fish. It is a living link between orbital mechanics and ecology. Yet the system's precision also exposes its fragility. Climate-induced changes in ocean stratification and temperature threaten to disrupt the formation of internal waves and nutrient upwellings. Without these periodic surges, plankton densities decline and the manta highways fall silent. Already, in regions where overfishing or sediment runoff alters water clarity, mantas are forced to travel greater distances between feeding sites. Tagging studies have revealed migrations spanning hundreds of kilometers as individuals follow faint cues of productivity across open seas. For an animal evolved to feed where current and terrain meet, these journeys carry enormous energetic cost. Still, when the conditions align, when moon, tide, and reef conspire, the old pattern returns. The current quickens, the water blooms with drifting life, and the mantas reappear as if summoned by the moon itself. They rise from the deep channels and assemble once more at the front, their movements slow and deliberate, their bodies carving invisible spirals through the haze. Plankton swirls in the vortices they leave behind, a living echo of the celestial forces that govern both sea and sky. As night descends, bioluminescent plankton trace the manta's paths in faint ribbons of blue-green fire. Each pass through the feeding vortex leaves glowing eddies that fade and reform, mapping the rhythm of the tide in light. The rays glide within this luminous storm, part animal, part physics, turning the ocean's pulse into a dance that links moonlight, gravity, and life itself. When the tide finally slackens, they vanish back into the dark, leaving only still water behind, waiting for the next lunar surge to set the plankton spinning again. In this cycle of light and flow, the manta ray stands as both participant and architect. It does not fight the current, it builds within it, shaping the tide's energy into nourishment, crafting order from turbulence. Here, beneath the moon's gravitational reach, the sea reveals its greatest secret, that survival is not always about strength or speed, but about knowing when to move with the forces that move the world. Along the tropical shoreline, under the glow of a near-full moon, the sand breathes with movement. What looks still from a distance is alive with fragile determination. Beneath the surface, a clutch of green sea turtle hatchlings stirs inside the nest, a shallow chamber carved by their mother 2 months before. For weeks they have waited in silence as their bodies formed within leathery eggs, absorbing yolk and oxygen from the sand's filtered air. Now the time has come. One by one they break free of their shells, using a specialized egg tooth at the tip of the snout, a tool they will lose within days. The chamber fills with the soft sound of scraping flippers and the rustle of sand. It is not the moon they sense yet, but temperature and vibration. Timing is everything. The hatchlings do not emerge randomly. They wait for the sand above them to cool. This usually happens after sunset, when the surface temperature drops and signals that the night sky, their safest passage, has arrived. The synchronization is astonishing. Dozens, sometimes hundreds, erupt from the sand at once, a tactic born of necessity. Alone, any hatchling is a meal. Together, they are chaos incarnate, a living flood overwhelming the senses of waiting predators. When they finally break through the surface, the world is blinding. The moonlight reflects off the wet sand, and the horizon glows faintly silver. To the hatchlings, whose eyes are highly sensitive to short wavelengths of light, this shimmering contrast becomes a compass. Instinct drives them toward brightness, a mechanism evolved over millions of years to lead them toward the sea. The sound of waves plays a secondary role, but it is the reflection of the moon and stars on the water's surface that seals their direction. The danger is that instinct was forged before beachfront hotels, street lamps, and human settlements existed. In many modern nesting areas, artificial lights now lure the young in the wrong direction, inland toward dehydration, exhaustion, and certain death. But on a wild, undisturbed beach, the ancient ritual unfolds as intended. Hundreds of hatchlings pour down slope, their flippers beating frantically, their bodies no bigger than a human hand. The sand is soft, the incline steep. Every few inches they stumble, flip, and correct course, leaving tiny tracks that glisten under the moon. The crawl lasts only minutes, but it is one of the most perilous journeys in nature. Crabs, herons, and raccoons patrol the dunes, waiting for the motion that betrays a new wave of arrivals. To minimize losses, evolution has balanced strategy and sacrifice. The nesting female, who may not see this beach again for years, laid over 100 eggs, knowing that only a handful will survive to adulthood. The rest are fuel for the ecosystem, feeding coastal scavengers and predators in a cycle as old as the species itself. By hatching en masse, the turtles saturate their predators' capacity to kill. It is a grim arithmetic, but an effective one: survival through overwhelming numbers. The beach narrows toward the surf, where the ocean breathes in steady, rhythmic bursts. Here, the tide's height becomes critical. On spring tides, those driven by the alignment of sun and moon, the water climbs higher, shortening the crawl distance. The hatchlings that emerge on these nights gain precious seconds. But the same lunar alignment that aids their sprint also awakens the hunters beyond the breakers. Tiger sharks, drawn by the scent of blood, fish oils, and disturbance, patrol the shallows. Their sensory systems are perfectly tuned for this event. The ampullae of Lorenzini, tiny electroreceptive pores scattered across their snouts, can detect the weak bioelectric signals emitted by struggling hatchlings even from several meters away. To the shark, each flailing turtle is a flicker of current in the dark, a signal of vulnerability. The moonlight only sharpens the picture. When the sea is calm and bright, the silhouettes of swimming hatchlings stand out against the lighter water above, turning the surface into a hunting stage. Not far from the surf zone, dolphins take position along the sandbar, another hazard in this gauntlet of survival. For them, the event is not a frenzy but a strategy. They know from generations of experience that certain nights bring easy prey. Using echolocation clicks, they map the clusters of hatchlings entering the shallows, intercepting the slowest or most disoriented among them. Even the waves play a role. Their refraction and turbulence sort the hatchlings, pushing weaker swimmers toward the edges where predators wait. What seems chaotic is, in truth, an ecological sorting mechanism, the sea testing which individuals can withstand its entrance exam. Yet the turtles are not defenseless. Their size, though small, gives them agility that large predators struggle to counter in breaking surf. The hatchlings use the wave energy to their advantage, timing flipper strokes with incoming swells to gain lift and speed. They are natural body surfers, riding turbulence toward deeper safety. Their shells, still soft and flexible, reduce impact force when tossed by waves. In evolutionary terms, the hatchling stage represents one of the most extreme examples of selective pressure in vertebrates. Only those that can coordinate vision, muscle strength, and timing within minutes of birth survive the first hour of life. For the survivors, the ordeal continues offshore. Once past the breakers, they swim tirelessly, propelled by an innate instinct known as the frenzy swim. This non-stop effort lasts for up to 3 days, carrying the young turtles into open ocean currents such as the North Atlantic Gyre or the East Australian Current, depending on their birthplace. These gyres act as conveyor belts of life, vast, slow-moving highways that distribute plankton, debris, and drifting seaweed mats. The turtles use these floating habitats as temporary refuges, feeding on small invertebrates and hiding from predators beneath the tangled sargassum. The moon continues to influence them even here. Lunar cycles regulate not only tides, but also the migration of prey. Many planktonic organisms rise toward the surface under moonlight and sink again at dawn, a behavior called diel vertical migration. The hatchlings follow this rhythm, adjusting their depth to match food availability and reduce risk from visual predators. In essence, the same moon that guided their first steps on land now orchestrates their survival at sea. Back on the nesting beach, the story repeats with every lunar phase. Adult females, some of which are returning to the same stretch of sand where they hatched decades earlier, emerge from the surf under cover of darkness. Using internal magnetic navigation, a biological compass keyed to Earth's geomagnetic field, they locate their natal beaches with astonishing accuracy, often within a few kilometers. The link between moonlight and nesting timing remains one of nature's quiet synchronies. The females often prefer nights of partial illumination, when tides are high enough to ease access to the dunes, but darkness conceals their silhouettes from land predators. Their journey is the mirror image of their offsprings, an ascent instead of a crawl, driven by instinct instead of panic. The nesting process itself is a labor of endurance. Using her front flippers to stabilize and her hind flippers as shovels, the female digs a pear-shaped pit nearly half a meter deep. Once satisfied with its shape, she deposits her eggs in slow, rhythmic clusters, each one cushioned in a chamber of sand. The act lasts nearly an hour, during which she enters a trance-like state, largely unresponsive to external stimuli. When finished, she buries the nest with deliberate care, tamping the sand to conceal its location from both sight and smell. Then, as silently as she arrived, she returns to the sea, leaving her unborn offspring to face the same forces that shaped her lineage for millions of years. When viewed from above, the entire process, from nesting to hatching, mirrors the cycles of celestial alignment. Lunar gravity drives the tides shape the beach births the turtles. Each generation depends on the same alignment of light and water, temperature and phase. The moon's glow, though soft, casts an invisible order on life along the coast. It determines when sand cools enough to signal emergence, when the surf rises high enough to shorten the gauntlet, and when predators gather to test the next generation. By dawn, the beach is quiet again. The sand is marked with the faint tracks of those who made it and the scattered remains of those who did not. The tide creeps upward, erasing evidence grain by grain. Out at sea, a few hundred hatchlings drift beyond the reef edge, their small bodies glinting in the sunlit water.
Somewhere among them, one will grow into a 300-pound adult, return decades later, and repeat the journey under the same moon. The gauntlet never ends, it only renews.
The moon's pull, the same force that shapes continents and currents, orchestrates this dance of survival with mechanical precision. In its pale light, life begins, life ends, and the line between both is drawn not by strength alone, but by timing, by instinct, and by an ancient rhythm shared between earth, sea, and sky. Under the moonlit surf, the green sea turtle remains one of nature's most enduring symbols of endurance. A creature whose existence is written in the language of tides, and whose survival depends quite literally on the light of another world. At the junction where river meets sea, the water never truly rests. It breathes with the moon. Twice each day, a pulse of energy races inland, a surge so powerful that it reverses the flow of entire rivers. These are the tide bores, traveling walls of water born from the gravitational rhythm between earth, moon, and sun. In most places they pass unnoticed, but in certain estuaries, the landscape amplifies their force. The banks constrict, the channel narrows, and the incoming tide piles upon itself, transforming the ocean's gentle rise into a fast-moving, churning front that charges upriver with a roar. For the fish caught in its path, it is chaos, a wall of shifting pressure and current that sweeps them helplessly inland. For the saltwater crocodile, it is opportunity. Here at the threshold between salt and fresh, these reptiles dominate the flux. The saltwater crocodile, Crocodilus porosus, is the largest living reptile on Earth, an apex predator capable of exceeding 6 meters in length and weighing over 1,000 kilograms. It is a survivor from an ancient lineage that predates mammals, birds, and most flowering plants. Yet despite its archaic form, it is not a relic. It is an adaptive genius, a hunter perfectly engineered for the dynamics of moving water. Its power does not come only from brute strength or crushing jaws, but from a profound understanding, born of instinct, of hydrology, physics, and timing. When the tide bore begins to form at sea, the crocodile is already in position. It has learned the pattern, not through reasoning, but through the repetition of countless lunar cycles. Every fortnight, when the moon aligns with the sun to produce spring tides, those with the greatest range between high and low, the boar returns, and the crocodile's ambush begins anew. The reptile drifts near the river mouth, body half submerged, limbs splayed. To the casual observer, it appears motionless, but within that stillness lies precision. Its eyes and nostrils break the surface, while the rest of its form remains hidden beneath the tannin-stained water. The surface seems to cradle it in calm, yet the animal is reading subtle signals, the vibration of the approaching tide, the shift in salinity, the rise in hydrostatic pressure that precedes the surge by minutes. As the boar rolls in, the river transforms from a languid current into a kinetic machine. Water folds back on itself, forming vortices along the banks. To smaller animals, these eddies are escape routes, places of temporary calm amid the turbulence. To the crocodile, they are anchor points. With a gentle tilt of its tail and an imperceptible yaw of the body, it slips into one of these pockets of slow-moving water. Here, it holds position without struggle. The tail, broad and muscular, acts like a rudder. Minor adjustments in angle allow the crocodile to stabilize against the shifting flow. Its skin, armored with dermal scutes embedded with sensory pits, detects subtle pressure gradients, changes in current direction, velocity, and the micro-disturbances created by swimming fish. These integumentary sense organs are so sensitive they can register the difference between a drifting stick and a darting mullet, even in complete darkness. The predator waits for the perfect moment. The boar front approaches, building like thunder. The fish ahead of it are frantic, their schooling patterns disintegrating under the compression of the current. They bunch together, pinned between the advancing wall of water and the shallow edges of the channel. This compression effect, the same principle that drives prey toward bottlenecks in nature, plays directly into the crocodile's strategy. Timing is critical. Move too early, and the surge sweeps the predator off course. Too late, and the fish are gone. As the leading wave crests, the crocodile releases its hold on the eddy. It pivots with a smooth, deliberate motion, a maneuver known as yaw steering, allowing the surge to slide along its body rather than strike it head-on. This rotation minimizes drag and positions the animal for attack. In a single pulse of its tail, it accelerates across the current, exploiting the velocity differential between the boundary layer and the main flow. The movement is short, explosive, and calculated. In that moment, hydrodynamics and muscle converge into violence. The strike itself unfolds faster than the eye can track. The crocodile's head twists in a fraction of a second, a rotational snap that converts stored muscle energy into torque. The jaw muscles, already among the most powerful in the animal kingdom, clamp shut with a force exceeding 16,000 newtons, enough to crush bone or shell instantly. But the crocodile does not merely bite, it engineers its attacks to the flow. The rotational strike aligns with the water's motion, allowing the predator to maintain stability even in chaos. Once the prey is seized, the animal uses the same current that delivered it to complete the kill. By rolling with the boar rather than against it, the crocodile conserves energy while ensuring the struggling fish remains pinned in its jaws. When the initial surge passes, the river settles into a high, fast-moving flow. The crocodile retreats once more to calmer water, another eddy, another pocket of relative stillness. Here it feeds. Its conical teeth, designed for gripping rather than slicing, hold the prey steady while powerful throat muscles draw it whole into the stomach. The digestive system of Crocodilus porosus is extraordinarily efficient. Its gastric juices are among the most acidic in any vertebrate, capable of dissolving bone and shell within hours. This biochemical ferocity allows the animal to consume nearly every part of its catch, leaving little waste. An essential adaptation for a predator that may not feed again for days or weeks. But feeding is only one part of the equation. The boar provides more than food. It is a transport mechanism. During strong tidal surges, crocodiles have been observed traveling dozens of kilometers upriver, riding the leading edge of the flood like a living raft. By conserving energy in this way, they extend their territorial reach deep into inland waterways where fresh prey awaits. When the tide ebbs, they reverse the process, drifting back toward the coast with minimal effort. In this way, the lunar cycle becomes a conveyor belt of mobility, a predictable engine of movement that links estuaries, mangroves, and riverine habitats across vast distances. The crocodile's ability to exploit this dynamic system depends on physiology as much as behavior. Its cardiovascular design allows it to remain submerged for long periods while waiting out the boar's turbulence. A specialized valve in its heart, the foramen of Panizza, enables blood to be rerouted during dives, conserving oxygen by supplying only critical organs. Meanwhile, its metabolism can slow dramatically, allowing the animal to survive hours without breathing, even in the low oxygen water that follows a churning bore. Evolution has refined this endurance over tens of millions of years, turning a once terrestrial reptile into an aquatic ambush engineer. From an ecological perspective, the saltwater crocodile's relationship with the tide bore exemplifies a broader principle. Predators adapt not just to prey, but to the physics of their environment. Just as peregrine falcons use gravity to dive, crocodiles use hydraulics to hunt. Their strategy is not a simple chase, but an understanding of flow mechanics. They exploit the boundary layers where current and stillness meet, the same zones where prey seek refuge. This convergence of predator and prey in the same hydrodynamic niche defines much of life at the river mouth. As night deepens and the moon climbs higher, the boar recedes into the distance, its roar fading into the rhythmic wash of the incoming tide. The crocodile drifts near the surface, its nostrils just breaking the air, its eyes reflecting pale lunar light. The estuary is calm again, but the pattern is set. The next spring tide will repeat the cycle with clockwork precision. For this animal, the moon is more than a distant orb. It is a metronome of survival. Each alignment of celestial bodies sends a signal through the ocean, through the river, and into the instincts of this ancient predator. By dawn, the crocodile has returned to the mangroves. It slides silently among the roots, the brackish water still swirling faintly from the night's surge. Around it, the ecosystem breathes again. Fish resume their migrations, crabs emerge from burrows, and herons stalk the shallows. All are unaware that the stillness is temporary. The tide will turn, the moon will pull, and the boar will rise once more. When it does, the crocodile will be waiting, motionless yet ready, the living embodiment of patience harnessed to physics. It is this combination of endurance, intelligence, and timing that cements the saltwater crocodile's role as the undisputed ruler of the tidal frontier. It does not fight the river's power, it partners with it. Each strike, each ambush, is calibrated to the rhythm of the earth itself. The moon's gravitational dance across the sky becomes the pulse of the hunt, a silent conversation between celestial motion and predatory instinct. In that partnership, evolution finds its most elegant form. Life not just surviving in the tide, but mastering it. The sea at night becomes a different world. The blazing hues of the reef fade to monochrome under starlight, and sound takes over where sight falters. Water moves softly against coral, and the faint rasp of sand grains sliding over one another is punctuated by the whisper of fins.
Out of this quiet, something stirs, a ripple of motion so smooth it could be mistaken for a trick of the current. Then, with a subtle change in angle, light catches an eye. A cuttlefish hovers in mid-water, arms folded close, skin alive with minute pulses of color that seem to move faster than thought. It is a creature built from contradictions, a predator and a lover, soft yet armored, ancient yet complex. And on nights like this, nights of the lunar calm, it gathers with others of its kind for one of the ocean's most intricate displays of communication and reproduction. The timing of these gatherings is no accident. Across coastal shallows and reef slopes, cuttlefish synchronize their spawning to the moon. Not every phase will do. The chosen nights come when the gravitational pull flattens the tides, a brief window when currents slacken just enough for delicate eggs to cling to coral, rock, or seaweed. On these nights, the water is thick with plankton and calm enough to allow vision without distortion. For the cuttlefish, vision is everything. Their eyes, shaped like commas, contain W-shaped pupils and sophisticated polarization filters that turn even faint starlight into usable contrast. Where most nocturnal hunters navigate by touch or scent, the cuttlefish sees the world in electric gradients of polarization, a dimension of light invisible to almost every other creature around it. Within this dim world, color returns, not as reflection, but as creation. The cuttlefish's skin is a living display screen composed of millions of chromatophores, iridophores, and leucophores layered like pixels in a flexible membrane. Each chromatophore contains a sac of pigment that can expand or contract in milliseconds, changing both hue and brightness. Iridophores lie beneath, reflecting polarized light to create iridescence,
while leucophores scatter ambient light, amplifying contrast in darkness. Through this anatomy, the cuttlefish writes language directly onto its skin, a grammar of flashes, stripes and ripples that convey mood, dominance and intention. As the moon reaches its zenith, the sea floor begins to shimmer faintly with movement. Dozens of cuttlefish, drawn by the same celestial rhythm, converge in the shallows. The gathering is tense, part courtship, part competition. Males display elaborate body patterns to attract females, their arms curling and unrolling in slow, deliberate waves. Each pattern carries layered information. A darkened mantle and spreading zebra bands signal aggression. A pale shimmer paired with rhythmic fin undulation advertises courtship. To an untrained observer, it looks like chaos. To the cuttlefish, it is conversation, a silent, fluid exchange conducted through light and posture. Females hover near patches of coral or eelgrass, evaluating the performances around them. They prefer males that can sustain complex displays while maintaining control of their shape and position, a test not only of fitness, but of cognitive coordination. Cuttlefish rank among the most intelligent invertebrates, capable of problem-solving, memory retention, and social manipulation. Here, that intelligence becomes visible. Dominant males patrol the open area, their patterns bright and confrontational, while smaller males employ deception. Some disguise themselves in female coloration, slipping unnoticed past rivals to court receptive females under their noses. These sneaker males mimic both the color pattern and the posture of females, hiding their true identity until the moment of mating. When they succeed, they dart in beneath the female's arms, transferring a packet of sperm, called a spermatophore, to a special pouch near her mouth, then vanish before the larger males realize the trick. The exchange lasts only seconds, but it leaves a genetic mark that will survive long after the participants are gone. Females may mate with multiple partners in one night, storing spermatophores from different males. Later, as she lays her eggs, she can selectively use or mix these contributions, a reproductive strategy that enhances genetic diversity and resilience in her offspring. The eggs themselves are small, dark pearls encased in protective jelly, attached in clusters to firm surfaces where they will develop over several weeks. Each one contains a fully formed embryo with chromatophores already functional, the young cuttlefish capable of camouflage within minutes of hatching. But for the adults, the lunar calm is not only about reproduction, it is also the stage for hunting perfected by physics. When currents slow and water clarity improves, plankton and small fish drift closer to the reef edge. For the cuttlefish, this is both opportunity and risk. The same visibility that allows it to see prey also exposes it to predators, sharks, groupers and eels that patrol the night in search of soft-bodied meals. Survival depends on deception. In seconds, the cuttlefish can vanish against its background, its skin replicating the precise color, texture and even depth cues of sand, coral or shadow. Yet camouflage is not invisibility, it is strategy. The cuttlefish uses its disguise not merely to hide, but to manipulate perception. When it hunts, the body remains still, arms tucked, fins fluttering in faint metronomic ripples. It scans the surroundings using its eyes independently, each rotating on a separate axis to build a stereo map of motion. Once a target is detected, a shrimp shifting beneath coral or a small fish drifting near the bottom, the cuttlefish recalibrates its approach. Rather than charge, it calculates. Its tentacles, two specialized feeding appendages, are coiled inside sheaths between the arms, loaded like springs. The strike must occur faster than the prey's escape reflex, faster even than its lateral line can register pressure changes. To achieve this, the cuttlefish approaches through silence, shaping the water around its body. Here, physics again becomes weapon. The animal's jet propulsion system, a muscular siphon that expels water with precise control, can create bursts of thrust or subtle pressure adjustments. By directing micropulses of water backward, the cuttlefish counters its forward momentum, keeping the surrounding flow laminar. This prevents the telltale pressure shadow that would alert fish with sensitive lateral lines. Only at the last possible moment does it switch tactics. With a single powerful jet pulse, it lunges forward, extending its tentacles in a blur. They uncoil and lock onto the prey with suckered clubs tipped with chitinous hooks. The impact is nearly silent. Before the prey can twitch, it is drawn inward to the beak, a black, parrot-like structure capable of slicing through shell or exoskeleton with surgical precision. Every strike is followed by stillness. The skin shifts once more, flashing a faint ripple of color, sometimes a mimicry of surrounding light, sometimes a pulse of polarization that may serve as communication to the cuttlefish nearby. These flashes are visible only through polarized vision, a secret signal invisible to predators and most prey. It is one of evolution's most elegant forms of encryption, a private language spoken in wavelengths. When the lunar cycle turns and the tides quicken again, the spawning grounds begin to empty. The adults, their bodies worn from exertion and the metabolic strain of reproduction, retreat to deeper water. Many will not survive the season. Like salmon in rivers, cuttlefish are semiparous. They reproduce once, then die. Within days or weeks, their bodies succumb to exhaustion and predation. But their offspring, incubating in their dark pearls, will hatch under the next moon, perfectly equipped to repeat the cycle. What emerges from this sequence is a portrait of precision, of biology synchronized to celestial rhythm and environmental mechanics. The cuttlefish's life is a constant negotiation between visibility and concealment, communication and secrecy, risk and opportunity. Its entire existence depends on mastering light, using it to court, to deceive, to kill. As dawn approaches, the last of the lunar glow fades, replaced by the first wash of sunlight filtering through the surface. The reef begins to reawaken. Parrotfish nibble at coral, plankton drift upward, and shadows dissolve in the brightening water. The cuttlefish, its body now pale and inert-looking, glides toward deeper refuge. Its color patterns slow to neutral grays, conserving energy and blending with the dim blue of the open sea. The moon, having orchestrated its brief but magnificent theater, withdraws its pull. Yet its influence lingers, in the eggs swaying gently beneath coral branches, in the rhythms of tides yet to come, and in the silent grammar of light that will guide the next generation. In the vast nocturnal ocean, where sound fades and darkness rules, the cuttlefish remains a creature of illumination, a master of communication written in shadow and shimmer. Its language is not spoken but seen, not heard but felt through the physics of light and water. Under the moon's quiet command, it becomes both artist and assassin, its life compressed into flashes of brilliance that vanish with the tide, leaving behind only echoes of polarized light in the dark.